opposite angles are congruent. So the given is, of course, that WXYZ is a parallelogram itself, and then angle ZWX plus angle WZY should equal 180 degrees, like all parallelograms, and that would be consecutive supplementary angles. Angle ZWX plus 90 equals 180 degrees. You can substitute it and it's still the same thing. And so if you subtract it from this, then angle ZYX should equal 90 degrees. And so your given is ABCD is a parallelogram. ABCD is a parallelogram given. Angle ABC plus angle ADC is 180 degrees. Consecutive supplementary angles. Angle ABC plus 90 equals 180 degrees, which is substitution, and angle ABC equals 90 degrees by itself because we subtracted it from this. Okay, so the third theorem states that if a quadrilateral is a parallelogram, then its consecutive angles are supplementary. So given that angle F is 90 degrees, we have to prove that the angles are supplementary. So angle F is 90 degrees given. Angle E is congruent to angle G, which is opposite angles are congruent. Angle E should equal angle G. That's the definition of a congruent segment. And angle E equals 90 degrees by itself, and that's substitution. So given that angle G in this problem is 90 degrees, angle F and angle H are congruent to each other. Opposite angles are congruent again. Angle F and angle H are the definition of congruent segments, and angle F should equal 90 degrees, which is substitution. So theorem number 4. If a quadrilateral is a parallelogram, then its diagonals bisect each other. So the given is that EFG is a parallelogram, and that angle FEH is congruent to angle FGH. So you write in your given, FS is congruent to SH, which is diagonals bisect each other. FS should equal SH, definition of segments, and HS equals 7 centimeters, and substitution. So ABCD is a parallelogram given. BE is congruent to ED, diagonals bisect each other. BE is equal to ED, definition of segments, and BE equals 30 feet, so substitution.
Standard number 2, make formal geometric constructions with a variety of tools and methods, such as compass and straight edge, string, reflective devices, paper folding, dynamic geometric software, etc. Copying a segment, copying an angle, bisecting a segment, bisecting an angle, constructing perpendicular lines, including the perpendicular bisectors of a segment, aligned segment, and constructing a parallel line to a given line through a point not on a line. Oops. And this is how you would copy an angle, a line. First you take a line, and then from your compass you would take your compass one point and put your other point right here. Without changing your compass, you would put one end over here, the pointy end, and then just mark. And then from there, that is where you would get your other point, and that's how you would copy a line. Bisecting a line. First you would take your compass, maybe put it over halfway and just make an arc. And then without changing your compass, you would do the same thing to point B. Without changing, make a huge arc, same length, and then connect both sides that intersect, and that will give you your middle. Bisecting an angle, you would first take your arc, your compass, put your point right here on point H, and then make a small arc right here. Once you make an arc where the 2 points with arc intersect, you would put it through, put a point there, and then you would label them. As you label them, you would put your compass here and make an arc right here. Without changing your compass, you would do the same thing you did from point J to point I. And from these two arcs, you would intersect them. You would create a line. That's how you bisect an angle. Like copy an angle, you would first take your angle. You would make an arc from point F, and as you make an arc, it should intersect in 2 points, and I will label them point H and G. From then, you would take this other line, and without changing your compass, you would make the same arc as you did for angle F. And then you would measure point H to G, and without changing your compass, you would put your point from here and make an arc here. And making an arc, you would intersect here, creating a line, and your angle should be the same. Okay, drawing a perpendicular line, you would start from point A, put the compass on point A, and then make an arc through the line, and I labeled them C and B. And it's the same type of process you would do when bisecting a line, but you're not bisecting this line. You would take your compass, put the point on C, and then I measured it from point C to A, and I made an arc there. And I did the same as I did on point C to point B, of course without changing my compass. And that's how I created a perpendicular line, because exactly it's 90 degrees here. It's perpendicular. Drawing a parallel line. You would start from drawing a line from point A to point B, and then from there, from point A, you make an arc. You should probably have an intersection, a point where your arcs and your line intersect, so that's point C. And you should have, your paper should look like this, with point D. And from then you will also make an arc from point B, and where the arc intersects here creates point E. And from you would measure from D to C, and without changing your compass, you would do the same thing here. From E, you would make an arc, and you would create, I think that's an F, but you would create point F, and from point B and F, you would create a line, and that's how you draw a parallel line. Standard number 3, you would learn how to construct an equilateral triangle, a square, and a regular hexagon that are inscribed in a circle. When you're constructing a square that's inscribed in a circle, you would first bisect the line. Remember, you would then draw a circle around the points, these lines, and then from there, you would draw a square. Each point that the line touches the circle. That's how you construct a square that's inscribed in a circle. Pretty easy, right? That's great. So when you're constructing a hexagon inscribed in a circle, you would first draw a circle. You have to find the midpoint of the circle first, of course. And then from there, you would draw little arcs around the circle. And then wherever the intersection points is, you would mark each and every one of them. And from there, you would connect each dots and you would create a hexagon. And that's how you construct a hexagon that is inscribed in a circle. Constructing an equilateral triangle inscribed in a circle. Equilateral triangle means that each angles are the same. So, first you would bisect the line, the same thing as you did for the square. And then from there you would connect these lines together first, and then you would have to find the midpoint of well, the middle of each side, like you're bisecting a line. And from there, you should probably get the middle point of the triangle, the center of the triangle. Then from there, you would draw a circle around the triangle at each point, and that is how you construct an equilateral triangle inscribed in a circle.
Standard number 4 is using coordinates to prove simple geometric theorems algebraically. For example, proving or disproving that a figure defined by 4 given points in the coordinate plane is a rectangle, proving or disproving that the point 1, the square root of 3, lies on the circle, centered at the origin and containing the point 0, 2. Okay, so the next vocabulary word and the last one is coordinate proof. It's a style of proof that uses coordinate geometry in algebra. So the example question we have is that the given is that triangle EFG has vertices point E is 0, 3, point F is at the origin, and point G is at 7, 0. H is the midpoint of segment EG. So we have to prove that the area of triangle HFG is half the area of triangle EFG. And so with the proof, we would prove that triangle EFG is a right triangle with height EF and a base FG. And so here I drew it and I plotted the points. So you get two triangles, like I said, and they're equilateral triangles. And so you would find the area of triangle EFG first using 1/2 base times height, and then you would plug in 7 and 3. Then you should get 21 over 2, or 10.5 square units. And then you would find the midpoint of EG to find point H, and you should get 3.5 point and then 1.5 as Y. And then since we know H is the height, the base has to be 7 units from this triangle. And so the area of triangle HFG is equal, you would have to find, of course, the area, so it would be 1/2 base times height. Plug it in, so the base is 7 and the height is 1.5 from here, and you would get 5.25 square units. And then if you divide the area of triangle EFG, which is 10.5, by 5.25 square units, which is the area of triangle HFG, you should get 5.25 if you divide it by 2. And that proves that triangle HFG is half the area of triangle EFG.